Hello and welcome back to another episode of Math with Sohn. Today we're going to be doing some linearization practice with an actual AP exam problem. Okay, so here's the scenario. We have a toy which is stretched, compressed on a spring, and it is released. And when it is released, it goes in the air because it's a spring. So in the experiment, students are to calculate the spring constant K of a vertical spring in a jumping small toy that initially is at rest on the table when the spring in the toy is compressed a distance x from its uncompressed length of L naught, blah, and the toy is released. The toy is reaching a maximum height of h, yada, yada, yada. Okay, so you can keep reading, but it's essentially wanting to know, derive an expression for the height in terms of mass, probably m, x, and k. You need to be very careful that you only use those variables. If you use variables that are not that, you will get 0 points, maybe 1 point if you're lucky. Okay? So the formulas, which you may not know yet if you're very new to physics, that would relate this would be for energy, mgh is the potential energy, like for gravitational potential energy. And 1/2 kx squared is the elastic potential energy of the spring. And whenever you have energy, it just converts from one form to another as long as there is no friction, which I'm betting if we read, the spring has negligible mass, and there's probably something that says that it has no friction or something like that. Okay, so we are going to set 1/2 kx squared, the elastic potential energy, equal to mgh. All right. As you advance in physics, that portion will get slightly easier, I would hope. But a lot of times they actually give you the formulas that you would have to use to derive. All right. So what are we trying to find? We're trying to determine an expression for the h. So we just need to solve for h. So if we solve for h, we will get h is equal to 1 kx squared over mg. You just divide by mg, and don't forget the 2. 1/2 kx squared times divided by mg, but I'm going to put the 2 on the bottom. Okay, so that is our expression. On the actual AP exam, you get tons of room to write. On anything provided by me, and most of your teachers, I would imagine, you get none because the formatting for worksheets off of AP Classroom is not as great as I would hope yet. I think they're going to get better eventually. Okay. With the spring compressed a distance of 0.02 meters, in each trial, the students obtain the following data. So we changed the mass and the height got changed, but what did not get changed was the compressed distance of x, okay? So that is the change in that. So I'm going to rewrite my thing. H is equal to kx squared over 2mg. We adjusted the mass, and as a result, the height changed. You can think of this as independent and dependent variables and make the dependent variable the y value and the independent variable the x value, but you don't have to according to AP, okay? But in this case, it already kind of worked out that way. So this is going to be my y value, will be my h's, and I'm going to peel off everything from the x value, which is going to be the m. So that means that we have kx squared over 2g, and then I have a 1 over m here, okay? So all of this is going to be my slope. My slope. It doesn't have to be, and I'm going to make 1 over m my x value. Now, I did not have to make 1 over m my x value. I could have made 1 over m times 2 and g and the x squared part. All of that I could have made a part of my x value. However, I like to make my slope big and my x value small. That's my personal preference. You could have added anything that is a constant into the x value. For instance, the x value that I have is 1 over m, but I could have made it 1 over m, g, with a 2, and the x squared. All of those were held constant. I could have made all of that my quote-unquote x value. Okay? I did not. I am making 1 over m my x value. So I need to put that here. 1 over m is my x value. And then my slope is going to be everything else, the k, x squared, the 2, and the g. So I need to, regrettably, do some math. The downside of these problems is it does involve a little bit of annoyingness. 1 divided by 0.02 is 50. and 1 divided by 0.03 is 33.3 repeat, and 1 divided by 0.04 is 25, and 1 divided by 0.05 is 20. The numbers are getting smaller. 1 divided by 0.06 is 16.6 repeat. Now, don't panic that the numbers look funky. We don't know what the y values did, but currently this looks like exponential decay for x, but maybe it's exponential decay for y as well, which makes it match up and therefore work out, okay? It says what quantity should be graphed such that the slope and the line of best fit would be allowing us to calculate the spring constant, not everything, but the spring constant with it. And I have, for the quantities, I have for x, we need 1 over m, and then against, I think it would be better, h against 1 over m. Okay, normally they have like blanks and they say what should you plot for the x and what should be plotted for the y, especially for AP1. Fill in one or both of the blank columns. You don't always fill in all of them, and we already did that. So part 2 done. On the axis, plot your graph and draw the line of best fit. Label your axes and indicate the scale. Okay, so you need to be very careful with that part. AP cares a lot about labeling the axis. We have 1 over m, which would be in kilograms. And then we have the height, which would be in meters. You need to include both the unit and the variable. Now you have to make sure that you scale it appropriately. You need to be more than half and more than half on both sides. So we need to make sure that we can go from 0.18 all the way to 0.49. AP normally doesn't really like page breaks, so we're going to try and make that fit starting at 0, okay? Trying to make that fit with 0. With ACE and other tests, maybe you can get away with that, but AP typically starts with 0. Okay, so if we got to go up to 0.5, essentially, we got 0.1, 0.2, 0.3, 0.4, 0.5. I think that is a good scale. 0.1, 0.2, 0.3, 0.4, 0.5. And if you want to put zeros in front, you can. You do not have to put kilograms, because that would be ridiculous, or meters. And then what about the x values? The x values have to go all the way to 50 as well. So we have 1, 2, 3, 4, 5. I am going to go 10, 20, 30, 40, and 50. Okay? So let's plot the points. I'm going to do the points with an orange marker. Hopefully they show up a little bit better. Maybe a pink highlighter. Make sure your dots aren't too big. Our first dot is at 50, comma, 0.5 almost. So 50, comma, 0.49 would be right about there. All right. And then our next dot is 33.3 and 0.34. They're almost identical. 33, perfectly halfway would be there. So 33 would be about there. And it goes up to 0.34. So 0.34 is right about there. Okay. Do be careful in the actual AP exam. They will check to make sure you plot points correctly, and you get points for, even if your data is wrong, if you plot points correctly, you can get points. So be careful. 25 and then 0.28. 25 is here, and 0.28 is there. So far, this looks pretty linear, so that's good. And then 20 and 0.19, 20 and 0.19 right there. And then the last one is 16.6 repeat and 18. So 16 is here, 0.6 would be there, and then 18 would be there. Okay? So ask yourself, is this mostly linear? Yeah. Ask yourself, do you have a straight edge? Because you need to now draw the line of best fit. I'm going to attempt to get a straight edge here. Oh, it's not going to work out very well. I got a whole bunch of box. I'm going to draw the line, and then I'm going to show you what a line of best fit should look like. It should look A, like a line, and B, you should try and have the line. I didn't do a perfect job. See how I have 2 dots here above? That's not great. It's not bad. It's pretty close, but I would have preferred to have 1 below, 1 above, then maybe 1 below and 1 above. But I do have this one below. See how that one's below? So there is a little bit of margin of error that they allow. So line of best fit drawn. Now what do we have to do? Use your line of best fit to calculate the numerical value for the spring constant. Okay, so numerical value for the spring constant, we have to A, find the slope here, which you need to pick 2 points that are not the data points. So I am going to choose here, and I am going to choose here because I can't choose that dot. All right, unfortunately, it looks like it goes through perfectly. So I'm going to choose these 2 points. I'm going to label these two chosen points. This one is going to be 10, comma 0.1. And then the next one is 50. We are counting by twos. 2, 4, 6, 8, 10. Yeah, so this would be, the next one would be 52, comma 0.52. Okay? So those are the 2 points you have to write out your y2 minus y1, not the actual formula, but you actually have to show your work for it. If you do not show your work, you get 0 credit because they know that you can do this in a graphing calculator. So that would be 0.52 minus 0.1 over 52 minus 10. I'm going to do that in my calculator. We don't like fractions, so 0.52 minus 0.1 divided by 42. I get a slope of 0.01. That is not my spring constant. Remember, that's just the slope. What did the spring constant, maybe all of the slope, more importantly, equal? Well, look at what we have in our slope. We have k, x squared, 2, and g, because of the way that I decided to do it. So that means 0.01 is equal to k, x squared, 2, and g. This is an important part in the video. The slope equals everything that the slope is equal to. We need to solve for k. You can either do that before or after plugging in stuff. I'm going to do it now. K would equal 0.01 times 2g divided by x squared. And then I can plug in everything I have that I know. Well, k is equal to 0.01. I know what 2 is. 2 is 2. I know what gravity is. And for AP, you're allowed to use 10 for gravity. Typically, you plug in positive 10, not negative 10, and which makes sense because the slope is positive here. And if everything else is positive, the slope must be positive. Okay? And then what is x? X was told to us in the very beginning. You got to find that sometimes within the writing. It's a very good reading test sometimes. Plug in 0.02 for x, 0.02, and then you square it. And if we do all that, you get 0.01 times 2 times 10 divided by 0.02 squared. You get a k value of 500. And for good measure, it would be newtons per meter for a spring constant. Okay, so we did that. That is part D. It was 500 newtons per meter. Now, AP does give a margin of error. They allow you to get probably somewhere from like 450 to 550. You're not going to know what that margin of error is by any means, but as long as you're doing things as good as you can, you should be okay. Part E, on these experimental designs, they normally ask you to do something else. That's not the focus of this video, so I am going to cut it short here. Until next time, stay positive, my friends, and I will see y'all later. Bye.